Hello everyone. Hello 151 particularly. I'll be uploading a new solution for Gauss-Seidel kasi the solution that I've uploaded before, na-realize ko ay na-negate ko yung buong admittance matrix, this one. So I'll be uploading one kasi I'm not sure kung tama yung intermediate values doon. But if you were able to access that and natapos nyo na yon, the solution is still the same. So I guess ang magbabago lang sa kanya ay yung intermediate values kasi magbabago yung madi-displace yung mga sagot by 180 degrees. Well, anyways, before I proceed with load flow and Gauss-Seidel, I'll orient you with this example muna, with this system, kasi this will be the system that I'll be using for Gauss-Seidel and Newton-Raphson, basically for the whole discussion on load flow. So what I have here is a 3-bus system with 2 generators, 1 generator on bus 1 and another generator on bus 3, and it is supplying 2 loads, 30 plus J40 MVA, 30 megawatts and 40 mVars on bus 2, and 50 plus J50 or 50 megawatts plus J 50 mVars on bus 3. Now I don't put much detail on that generator on bus 1 because I'll be using that bus as a slack bus. So for kung ano bang ibig sabihin ng slack bus, please visit the other video regarding load flow buses. Now on bus 3, I put 30 megawatts on the generator. This basically tells you that I want that generator to produce 30 watts and inject that 30 watts into the system. So basically, magpo-produce siya ng 30 watts and then that 30 watts will be injected into the system. I also want this generator to have to produce a bus voltage on bus 3 of 1.01. As much as possible, I want to have that 1.01 per unit voltage on bus 3. So I took the liberty of developing the impedance diagram of this network here. So to simplify things, ang ginawa ko na lang ay put an impedance of 0.1, J.1 on the generator on bus 1 para lang makita niyo yung effect on the admittance matrix. And I took the liberty also of assuming an ideal generator on bus 3 para hindi na natin poproblemahin yung impedance niya. And then between any 2 buses, it is connected by lines with an impedance of 0.2, J.2. So forming the admittance matrix of this, basically the off diagonals, the contents of the admittance matrix on the off diagonals on cell 2 1 row 1, cell 1 2, cell 1 3, cell 2 1, cell 2 3. That's basically the off diagonals. Cell 3 1 3 2, those are the off diagonals. That's the negative of the admittance of the lines connecting them, connecting 1 2, connecting 1 3, connecting 2 3. So that's the negative of the admittance of the inverse of J.2. So the inverse of that is negative J.2. Negative of that is the inverse of that is negative J5. And then negative of that is J5. Now for the diagonals, it's basically the summation of all of the admittances connected on the buses. So for bus 1, it's the summation of all of the admittances. So 1 over J.2 plus 1 over J.2 plus 1 over J.1, that is negative J20. For bus 2, it's 1 over J.2 plus 1 over J.2, it's negative J10. And for bus 3, it's 1 over J.2 plus 1 over J.2, it's negative J10. Of course, if you have a generator impedance on bus 3, on this one, so we'll be adding the admittance of that also on bus 3, so that means it will be 1 over j.2 plus 1 over j.2 plus 1 over the impedance of the generator. But in this case, I just assume that it is ideal. Okay, so this is your admittance matrix. If you were not able to follow that, I suggest you go back to your notes on how to form the admittance matrix. Now, for this example, I'll be using bus 1 as a slack bus. So that just means that for bus 1, I'll assume that the voltage on that bus would be 1 angle 0 degrees. So the point of that is that for me to have a reference for all of the other buses, such that if I have a voltage of 0.95 angle 0 on bus 2, so that just means that the voltage on bus 2 is 95% of whatever is the voltage in bus 1. Of course, what will happen there is, well, of course, that would be affected by the base values. Now, for the other two buses, bus 2 and bus 3, if you look at bus 2, it has a load. So it's a PQ bus. It just tells you that on that bus, I want to have a certain P and a certain Q. So yeah, so I want to have a certain P of 30 megawatts and a certain Q of 40 MVARs. Of course, our analysis will always be in per unit, so we'll be using 100 MVA base to get a 0.3 and 0.4 J.4 per unit P and Q on bus 2. Now on bus 3 has a load of 50 plus J50 MVA and a generator that produces 30 megawatts. So I have two options. I can treat bus 3 as a PQ bus or bus 3 as a PV bus. So what's the difference? If I treat bus 3 as a PQ bus, then I'll be forcing the network to have a P and a certain P and a certain Q. So that makes my voltage magnitude and voltage angle variables on that bus. However, if I assumed a certain P and if I assume that bus 3 is PV bus, then I'll be forcing the network to have a certain P and a certain V magnitude. Meaning, the Q and the voltage angle on that bus will be variables. So, for further discussion on the difference of load flow buses, so I suggest you go back to that separate video. Okay. However, for bus 3, we'll be treating it as a PV bus because of the generator. You want your generator to operate at a certain voltage magnitude. So you, as much as possible, you want to maintain that voltage there. So you want to maintain that 1.01 voltage there. You want to keep that. So instead of treating it as a PQ bus, you want to keep the voltage. So we'll just treat that as PV bus. So that's basically the example that I'll be using for Gauss-Seidel and Newton-Raphson. Now, your load flow, whether it's Gauss-Seidel or Newton-Raphson or any other load flow methods, will always start with initialization of values. So the idea of initialization of values is, well, we don't know yet what are the voltages here. We just know that bus 1 is my slack bus, so I'll be assuming that it is 1 angle 0. All the other voltages in bus 2 and bus 3, I do not know. So for initialization, we'll be assuming a value for the voltage. And the safest assumption is to use flat voltages or 1 angle 0. So, or 1 angle 0, these are your flat voltages. So for bus 1, 1 angle 0, well, it's a slack bus, so every time it will always be 1 angle 0. Now for bus 2, for initialization, I'll be using 1 angle 0 flat voltage. For bus 3, I can use 1 angle 0. However, take note that we treat bus 3 as a PV bus. So that means we'll be keeping its voltage magnitude. So instead of 1 angle 0, we'll be keeping the 1.01 voltage magnitude. And then let 0 degrees as the variable. So that's how you initialize the power flow solution. So that's basically iteration 0, initialization. Now, before doing the iteration 1, I just put it here. Let me just explain what's the idea behind power flow. So power flow is like doing KCL nodes. So I'm pretty sure that you're all familiar with KCL in nodes. Basically, it's the summation of the current going in a node is just the same as the summation of the current going out. So power flow is just like that, but instead of summing currents, we sum power. That is, if this is your node, if this is your node, so all of the powers that is going in that node, that's 30, 20, and 10. So you have 30, 20, 10, so that's 60. All of that power going in will be going out, so that's 60. So that's the idea of power flow. It's just like KCL, but instead of summing currents, you just sum power. So generally speaking, this illustration here is just the same as this one. So I'll be using this convention for both Newton-Raphson and Gauss-Seidel. So all of the power injected into the system by your generator or load will be equal to the power going out of that bus and going into the network. So if I have a generator that is injecting 10 megawatts, then that 10 megawatts will go into the network. Of course, it makes sense that way. Okay, so for example, let's look at bus 2. So for example, in bus 2, you have the S injected into the network from your generator or load is equal to the power going into the system. So you have some power going from bus 2 to bus 1, some power going from bus 2 to bus 3. So it's basically this one. You have some power going from bus 2 to bus 1 and some power going from bus 2 to bus 3. And that would equate to your power that is injected. Now take note that on bus 2, that power is from a load. So it's injected by a load, or it's basically a negative injection. But I'll show that in the iterations. Now, okay. So sir, how do we form the equation for this one? Of course, your power is a function of voltage and current, but we're not familiar on how to do KCL with the voltage parameter. So let's go back to the summation of currents. So if we solve for the currents, these currents going from the bus 2 to the other buses, take note of the direction. I want you to take note of the direction. It's going from 2 to 1, 2 to 3. So that is under the assumption that 2 is higher potential than 1 and 2 is higher potential than 3. So if you solve for this current from 2 to 1, so it's basically this voltage 2 minus voltage 1. It's basically the voltage drop between those two buses. Then multiply it by its admittance, you get the current going from 2 to 1. Then take note, this is admittance of the line. I use small y. And then if you look at the voltage drop between 2 and 3, so that's V2 minus V3, multiply it by the admittance between 2 and 3, small y, admittance of the line, then you get the current at that line, 2, 3. Let's see. So now we have the current here. If you get the summation of that, that's basically all of the currents going into the system. And then you equate that into current injected. So your current on the injected side is given as a function of S. So for the current, you just divide it by the voltage V2, then you conjugate that, you get the current. So that's how you solve for the current. So basically now you have this first equation. We'll actually be working on this equation. You can distribute the voltages on this wise. So you have a V2 YU21, negative V1 Y21, you have a V2 Y23, then a negative V3 Y23, and then you have the S injected on bus 2 conjugate divided by the V2 conjugate. So now you have that. So if we rewrite this equation, you now have this equation in V1, V2, and V3. Now, if you look closely at this equation, what you have is a negative V1 Y21, and of course this is also equal to V1 times negative Y21. And what's special about that is negative Y21 is basically your Y21, your element on the row 2 column 1 of your admittance matrix. So now it's capital Y. If you look at V2, it's basically the summation of all of those connected on bus 2. So it's basically Y22. And if you look at on that one in V3, so you have a negative Y23. So it's basically capital Y23. So all of these parameters, all of these admittances can be found on your admittance matrix. That's why the admittance matrix is very important. I guess that's also the reason why I am repeating this video, because I negated the whole admittance matrix before. So you equate that to your S injected conjugate divided by V2 conjugate. So now you have this all in terms of the elements in the admittance matrix. You have this. And if you isolate the S injected here, basically if you multiply both sides by V2 conjugate, you'll get this equation. And now from your KCL that is in terms of currents, you now have something that is in terms of, well, it's not KCL because this is in terms of power, but yeah, you now have your formula for power flow. So this will be your working formula for solving this. So it's basically V2 conjugate times the summation of the currents. These are the summation of the currents is equal to S conjugate. Take note, this is S conjugate because our solution is in terms of V conjugate I and not VI conjugate. So that's it for initialization and KCL. So this will be the concept that I'll be using for both Gauss-Seidel and Newton-Raphson. I'll be finishing this example for Gauss-Seidel, and then later on I'll be uploading one for Newton-Raphson. Okay.